In the last lecture, we looked at radiative transfer in enclosure and we looked at a few examples of non-gray surfaces. We gave example of a Dewar flask, where the heat leakage into the flask was influenced by the spectral variation emissivity of the silver surfaces on the inside the flask. And the second example we gave was related to the tungsten filament lamp design, where also the design of the filament was influenced by the fact that the emissivity of tungsten was not really independent of wavelength. Okay. Now, these are very simple examples. We also looked at third example of selective surfaces. To control temperature in space, and we saw how in space you can maintain a surface at a very high temperature or very low temperature by controlling the spectral variation of absorptivity to the surface. All these are very simple examples, involved only essentially one surface impinging solar radiation impinging surface or two surfaces like Dewar flask. Now, let us go back and look at the Dewar flask example in terms of the spectral nature of the radiation. And if you draw a simple electric analogy, now at a spectral level, not at the total level. So, the two surfaces, two parallel surfaces now. So, F12 is 1 and let me just, the first is 1 by epsilon lambda 1 A, then this will be 1 over A is the area of the parallel plate, and finally, we have 1 minus epsilon lambda 2 by epsilon lambda 2 A, and finally, you have the surface 2. So, this expression can be written as heat transfer in the range lambda to lambda d lambda from 1 to 2 as E lambda b 1 minus E lambda b 2 divided by 1 by epsilon lambda 1 plus 1 by epsilon lambda 2 minus 1, of course, into area of the plates. So, this is for the interval lambda double. If you want total heat transfer over all wavelength, then you have to integrate this over d lambda. So, this also has to be integrated, and this integration can get quite complicated. But in the simple case that we dealt in the last lecture, we assume that epsilon lambda 1 is b into root T 1 by lambda, and surface 2 was again the same material, but at a different temperature. Then we used an approximation that since the emissivity of silver surfaces is very small, and the reflectivity is very large. So, this term is very large. So, we neglected this term. Okay. And on neglecting this term, the expression we got between two parallel plates was E lambda b 1 minus A lambda B 2 into A divided by 1 by epsilon lambda 1, which goes as root lambda by T 1 over B plus 1 over B root lambda B by T 2. And remember, root lambda is really common to them. So, this can be simplified to write as one over root lambda goes above, and below we have, and you can write A above, you can take also B above, nothing but 1 over root T 1 plus 1 over root T 2. Now, this can be integrated suitably, and we also already discussed the results obtained by this integration, and we showed that the heat transfer between two surfaces need not be proportional to temperature difference and can behave in rather unusual ways, and in particular we showed that as the temperature difference changes from a very low value to high value, in this case it was 300, actually the heat transfer rate, which should be 0 at 0 delta T, went up and then came down, reached the maxima around 150 K. So, all this occurred because of the spectral dependence and temperature dependence of emissivity of these surfaces. But let me illustrate a somewhat simpler example. This is a little complicated. Suppose a surface in plate 1 and plate 2, let us say this was a metal and this was black. So, this is a somewhat simpler example than the previous one, and so what happens here is that your equation simplifies to you have only this one, epsilon lambda 2 is 1. So, that cancels everything out, you have d lambda here. So, this can be written as q 1 2 as 0 to infinity epsilon lambda 1 E lambda b 1 minus epsilon lambda 1 E lambda b 2 into d lambda, because area is still there, which we cannot forget. Now, this follows very close to what we had done earlier when discussing the emissivity and absorptivity of metals. So, we can write E lambda as 1 as B times root T 1 by lambda. So, this equation here becomes 0 to infinity root T 1 by lambda A lambda B 1 minus 0 to infinity root T 1 by lambda E lambda B 2. So, this kind of analysis we have done before. We know that this is a function primarily of lambda t when you divide by t to the power of phi. We saw that earlier. So, as before, we will multiply up and down by t 1 and get this to be a function of t to the power of phi, and if you do all that, we get a result which should be quite familiar to you based on what we done earlier. So, what will happen is you get B here, and actually you get a B tilde actually. So, let me write down the whole thing B, and you will get T 1 to the power of phi sigma minus T 1 to the phi sigma here T to the power of 4.5, and what you have inside is an integral 0 to infinity, this integral which is a function only of lambda t d lambda t. So, this is a number which can be evaluated very easily, and usually is combined with this we did it earlier, and we call it b tilde along with sigma. So, we are left finally with so, this must be compared with this is metal and a black plate. If you have two black plates, then all of you know, of course, area is also here, I am sorry. Two black plates, and this is nothing but so that is the difference introduced by one metal being there in the top side. So, it increases the emissive power of the metal from 4 to 5. Then on this side, what is happening is that the effect of changing T1 is affecting the radiation absorbed from T2, because this can also be written if we now temporarily remove the simple expression we have here. So, we now write this as very simply as epsilon function of T1 to the power of 4 into sigma minus sigma alpha a function of T1 T2 into T1 T2 to the power of 4. This is how it should be, because in the case of metals, you must recall that alpha is not equal to epsilon. That was a fundamental result we had derived, that metals being non-gray, you cannot assume that the total hemispherical absorptivity is equal to total hemispherical emissivity, that you cannot assume. So, when alpha not equal to epsilon, then you have a result which is of this kind, but you recall that of course, that this could be written, and if sigma is absorbed in that definition as b tilde into T 1, that becomes this, and this is b tilde under root T1 T2, and hence this becomes. So, that is how this emerges. So, these two results are the same really, but derived in two different ways, and it clearly tells you that the traditional assumption that emissive power goes as 4th power of T is only true for black body. The bodies are not black and not gray, then you can have emissive power having powers larger than 4 or even less, depending on how the emissivity and absorptivity of that surface depends on wavelength. Now, let us take one more example to illustrate this unusual behavior. Let us look at shield. Suppose you have two black plates and you put a shield in between, which is metallic. Now, why would you put a metallic shield? Because we know that metals have the property of having low emissivity. So, they are good reflectors. So, they will reflect the radiation and reduce the, hence reduce the emission. So, let us draw the electrical analogy here. So, you have E lambda B 1 here, there is no surface resistance, emissivity equals 1, straight away you go to the geometric resistance, and then you come to the metal here, which will be 1 minus epsilon lambda 3 A, and then you have the other surface of metal, both surfaces are to be counted. So, there is another surface of metal here, 1 minus lambda 3 by lambda 3 A, and of course, finally, you have other surface also with no surface resistance, only geometric resistance 1 over A. Finally, you come to epsilon lambda B 2. So, this is the electrical circuit, and so you can see that the simple way to understand this problem is that epsilon lambda B 1 minus this point, which is epsilon lambda B 3 point. Okay. So, this point, the flow of current will depend on epsilon lambda 1, which is 1. So, it really depends on epsilon lambda 3. Similarly, on this side, heat going from the metal to the other plate will only depend on emissivity of the metal, because the two plates have emissivity equal to 1. So, that is the interesting situation we are in, that the current flow from plate 1 to this is equal to that, but this we must do over the entire wavelength range, not just. Okay. So, now we have to ask what is temperature of the shield T 3. So, this surface 3 the shield is. Now, the shield temperature has been such that the heat flow from 1 to 3 has to be equal to heat flow from 3 to 1, because in steady state the thin metal here cannot retain heat. So, whatever heat it gets from surface 1 to 3 has to go into the other side. Now, if you recall the discussion we had about 10 minutes ago, this expression now can be written. So, we are done already. So, we will just write the answer. So, we will write the relation for emission from surface 1 is sigma T 1 to the power of 4 minus what is emitted by the plate and absorbed by the black plate will be nothing but sigma T 3 to the power of 5, because the emission from the metal is like T to the power of 5 proportionality. Of course, there will be a B tilde here, which we have to remember, and this has to be equal to the energy that is emitted by 3 and that emission is absorbed by the plate 2, and the plate 2 emits back so much. Okay. So, the radiation that is emitted by 1, this is emitted by 1 and it is absorbed by 3, and okay, let me write a little differently here, so that we appreciate better. So, let us try in terms of emissive absorbed will be easier to appreciate. So, this is the radiation emitted by 1, what is absorbed by 3 is alpha 3, and the radiation emitted by 3 is epsilon 3, and all of it will be absorbed by 1, because 1 is a black body, and here is the radiation emitted by 3, all of it is absorbed by 1, and minus the radiation that is emitted by 2 and absorbed by 3. Let me just clear that a little bit. So, the balance is that the radiation emitted by 1 sigma T1 to the power absorbed by 3 minus what is emitted back by 3. This flow has to be equal to radiation emitted by 3 and what is coming back from 2, which is sigma to the power 4 and absorbed by 3. So, if you finally write down what is T 3 to the power 4, notice that sigma will cancel out on both sides. So, T 3 to the power 4 will come out as, here 2 epsilon 3 is there, do not forget, and you will have here alpha 3 into T 1 to the power of 4 plus T 2 to the power of 4. So, the final answer really is that T 3 to the power of 4 is alpha 3 by epsilon 3 into T 1 to the power of 4 plus T to the power of 4 divided by 2. So, the metal shield between two black plates will have temperature which depends on the temperature of the two plates, but depends on the ratio of alpha 3 to epsilon 3. Now, do we know alpha 3? The answer is not quite. As a matter of fact, we have a little bit of problem here, because this alpha 3 is not same as this alpha 3. Now, this is an interesting issue you must look at, because the radiation that is absorbed by 3 from 2 will be somewhat different from the radiation absorbed by 3 from 1, because 1 and 2 are not the same temperature. Okay. So, so we have to give a slightly different notation here, otherwise, so we will go back and slightly modify this to suit our, yeah. So, let us now recall that for metals, absorptivity goes as emissivity equals absorptivity goes as B by root surface by lambda. So, that is what we had already looked at. Okay. So, because of that, we also derived this earlier, that alpha goes as an epsilon first. Let us look at epsilon. So, because of this, you know that epsilon goes as a constant times T of the surface, and alpha goes as the same constant times root of surface temperature and the incoming temperature of that radiation, assuming that is a black body radiation. Given this, now we will write down what is emitted by 1 as sigma T 1 to the power of 4, and what will be absorbed by 2 will depend on temperature of 2 and temperature of 1. So, this will be B tilde root of T 1, T 2, T 3, because T 3 is the temperature of the let us remind 1, 3 and 2. So, the 3 is the metal. So, what it absorbs will depend on the temperature of the emitter and the to absorb. Now, minus what is emitted will only depend on B tilde and T 3 sigma T 3 to the power of 4. This will be equal to, on this side again what is emitted is only B tilde emissivity times emission. Now, what is absorbed here will depend on B tilde and root T 3 T 2, because these are the two temperatures involved here, and what is emitted is T 2 to the power of 4. So, once more sigmas are cancelling out very nicely. B tilde is also cancelling out, is common to all of them. So, what you obtain as 2 T 3 to the power of 4 is equal to root T 3 T 1 to the power of 4.5, that these two, plus again root T 3 and T 2 to the power of 4.5 divided by 2. So, you can take the root 3 out here. So, I am sorry, by 2 is not necessary now, I will come later. So, now you take the 2 down and this T 3 this side. Finally, you get T to the power 5 here, I am sorry, this should be 5, because T 3 to the power 5, 4, 4 and 1 5. So, now you take root 3 back here, now we will get T 3 to the power of 4.5 is equal to T 1 to the power of 4.5 plus T 2 to the power of 4.5 by 2. So, this is the final result, which is for a metallic shield between two parallel plates. So, temperature of a metallic shield between black plates. Okay, to ensure that our understanding of the problem has been quite good, we will look at one more example, which is the counterpart of this. Now, suppose you have a two metal plates and a black shield. So, you have two metal plates and black shield. If you have got familiar with this approach now, you can write by inspection that radiation emitted by one and absorbed by the shield will be here T 1 T 3 minus what is emitted by shield 3, that is here. So, this is the radiation that is emitted by one and absorbed by 3 the black shield. So, you have to slightly correct this, 3 the black shield. So, what is emitted by 1 is V delta T 1, that is the emissivity of metal times the black body emission, minus what is emitted back by 3. So, if you are doing a heat balance of 3, this is what 3 will absorb emitted. Similarly, what is emitted by 3 is this, and what is coming back from the metal and absorbed black shield, what is coming from metal is B delta T 2 times sigma T 2 to the power of 4. So, this is what is emitted by the metal, and the entire thing is absorbed by the black shield. So, here you can see that you have sigma cancelling out and you have T 3 to the power of 4 twice of that is equal to V delta T 1 to the power of 4.5 plus T 2 to the power of 4.5. So, you can see that in this case the result is somewhat different from what we got for the metal shield between two black plates, and this is not surprising, because what you are getting here is the fact that the black shield emits as T 3 to the power of 4. So, final result must depend on that. While I am sorry, this is T 1 to the power of 5 here, I am sorry. while the emission from the two metal plates top and bottom will be as T1 to the power of 5. And the current flow will depend on both the value of B tilde here and the way the metal emits, the two metal plates emit. Okay. So, the way to understand this problem is that the metal plate emission will govern these values and the black plate emission is governed by T to the power of 4. So, this gives you two examples here, one in which there were a metal shield in between two black plates, the other the black shield with two metal plates, and the results are somewhat different, indicating the important role played by the spectral variation of emissivity and absorptivity of the material. Now, it is worth looking here and understanding the fact that in this derivation the absorptivity of the metal played no role, because we were doing heat balance on the black shield. The black shield absorbs all the emission from the metal and it emits like a black body. So, this difference is a current flow into the black shield, and when on this side this is what black shield emits, and what the black shield absorbs is all the radiation coming from the metal on the other side. And so, this result is somewhat counterintuitive, but still a very useful result to have. Now, so far we have been dealing with cases where the surfaces are 1 or at the most 2, but we should also know how to extend this derivation to situation when the number of surface in the enclosure is more than 2. So, we want a general formulation which we must have, and this general formulation of an enclosure with n non-gray surfaces. So, if you have an enclosure with n non-gray surfaces, then for the jth surface the radiosity will be defined as the emissivity of the jth surface times the black body emission of the jth surface plus what is reflected of the radiation irradiation on the jth surface. And the radiation of jth surface will nothing but what is leaving the kth surface, and after applying reciprocity you have f j k here, and this is sigma k 1 to n. So, this is all similar to what we did for gray diffuse isotopic enclosure, except that now we are treating everything at a specific wavelength, okay, specific wavelength. Now, so you can now derive what is q lambda j, which is b lambda j minus h lambda j, and this is epsilon lambda j minus 1 minus epsilon lambda j into E lambda B j minus B lambda j. All this is very similar to the gray case, except that now we are treating results at every lambda. Now, what is q j? Ultimately, you are interested in q j. The q j is equal to 0 to infinity epsilon lambda j by 1 minus epsilon lambda j into E lambda Bj minus So, although most of the results are very similar to the Gray case, but you must remember that Qj equal to 0, an adiabatic surface, does not imply that Q lambda j is 0, because Qj by definition is 0 to infinity Q lambda j d lambda. But this is 0 does not mean this is 0, because all you are saying is the integral is 0. The integral is 0 if Q lambda j is negative for some lambda and in some other range of wavelength it is positive. So, it is possible for this integral to come to 0, because Q lambda j is changing sign. And this is quite common in many examples like furnaces, that in a certain wavelength range the surface gains energy by radiation, in some other wavelength range it loses energy by radiation. So, the integral over all wavelength is 0. So, this is what poses a special challenge in solving enclosure problem with non-gray surfaces. If one of the surface in the enclosure is adiabatic, then all you know is this integral is 0. That does not mean these two are equal. So, we cannot use this equation to infer anything about E lambda B j or B lambda j. So, all you can do is do an iteration. So, iterative techniques are the only technique available. You guess a temperature. So, the non-gray enclosures, the procedure is first guess Tj, calculate Qj, then if Qj in a given surface is not 0, if Qj is not equal to 0 in an adiabatic surface, you need to modify Tj. So, you go on modifying the temperature until that surface which is adiabatic has Qj, not till Qj is 0. So, this is a fairly tedious procedure, and if there are n surfaces in the enclosure, and in some of them temperature is specified, let us say in S surfaces temperature is specified, and in n minus S surfaces Qj is specified, then you have to go on adjusting all these n temperature, all these n minus 1 temperatures until Qj's reach a specific value. So, you can imagine that this procedure is not simple. It involves changing many temperatures in the iteration procedure until Qj is either 0 or some other number which is provided in advance. So, this iteration may not converge easily, but there are powerful mathematical techniques available to ensure that you are indeed converging to this specified value. For example, you can define error as the value of Qj you want minus Qj you have guessed, and if the guess value is less than the value given, then you know that the temperature of the concerned surface is too low, so increase it. Then it is possible that Q gas becomes larger than Q j, then you decrease it. It is like the root finding algorithm that you all use for solving equations, nonlinear equations. So, you have to ultimately make sure that the guessed value of Q j and the actual value Q j specified converge rapidly. But today with availability of very fast computers, it is possible to achieve that kind of convergence fairly rapidly, because it involves good initial guess. In all iteration techniques, you must remember that the initial guess is very important. You cannot assume arbitrary temperatures and expect your technique of iteration to converge to the right answer. There has to be some experience and expertise in guessing the temperatures of the surfaces with heat specified in a clever way, so that you get the heat transfer value quite close to the number specified. So, it requires some expertise. So, that is acquired quite easily after doing the iteration couple of times. Now, to illustrate the importance of non-gray surfaces, I will once more go at two infinite parallel plates which are not gray. So, epsilon 1 and alpha 1, epsilon 2 and alpha 2. Now, you can derive the heat transfer between these two surfaces either by following the spectral model and deriving it, or you can do it by ray tracing. Ray tracing is a powerful physically understandable concept. Now, ray tracing is getting very popular today because of the fact that computers are quite powerful in terms of the speed, and so it is possible to actually do radiative transfer calculations just by following photons, just tracing photons from their birth to their death. You just start with the photon emitted by one surface, keep following the photon as it reflects, and ultimately once it is absorbed, that life of the photon is over, and you count the last place where the photon was absorbed as having gained heat, and then you look at another photon emitted by another surface. So, good geometric ray tracing software along with what is called Monte Carlo technique can solve any complex problem by merely following a large number of photons, maybe 10,000, maybe 100,000 or a million photons, and doing a statistical average. Now, this technique does not give you any physical insight, but it is a very useful technique to deal with problems with complex geometry, problems with complex spectral variation. So, it is getting more and more popular, especially now there are standard Monte Carlo packages available, which will do the job of generating random numbers to make a decision whether a certain photon is absorbed or not absorbed. So, it is good to understand a given problem from the perspective of ray tracing. So, that I will do with this example. Now, notice that surface 1 is emitting radiation. So, this much radiation is emitted, and each surface 2, and there is a probability that is absorbed is so much. But if it is not absorbed, this emission will be reflected by surface 2. Once it is reflected, we look at when it will come back again, it will come back with reflect surface 1, then it is absorbed by surface 2. So, this process can continue. So, this is no reflection, 2 reflections, then you can add here 4 reflections, which will be like this. So, this can extend. So, this all of you can see that ultimately you are left with the infinite series, because all of them contain a common term, and so it will be 1 by 1 minus so that is the radiation leaving 1 and is absorbed by 2. Similarly, radiation leaving 2 absorbed by 1 will be a similar expression like this here. So, net heat transfer between the two surfaces based on this result can be written in a very elegant and simple way. So, this is general result for a non-gray surface where the emissivity and absorptivity are not equal, and clearly demonstrating the role played by reflection in the denominator, emission and absorption in the numerator is spotted very clearly. Suppose we have a gray surface, then of course, alpha 1 equals epsilon 1, alpha 2 equals epsilon 2. So, the epsilon 2 becomes common here, this 1 anyway cancels out. So, then you can easily show that this is same as what we have derived for gray surfaces. So, what you have done really is there is a general relationship when alpha 1 and epsilon 1 are not equal, non-gray, and ultimately looked at how this simplifies when you make this assumption. So, this result is more general, the one above, and if you can estimate from some property data epsilon 1, alpha 1, epsilon 2, alpha 2, then of course, you have got a more accurate result than this, which assumes gray surfaces. You can also derive the same result by so many other means, but it is important to recognize that the non-gray situation occurs more commonly in the industry. There are very few truly gray surfaces that you encounter in the real world, and you have to deal non-gray surface. And I will just illustrate a typical example of a solar collector. All of you are familiar with solar collectors, which are used for collection solar radiation in solar water heaters. So, if you look at a solar collector, the most important component of solar collector is the cover, which is usually glass, it can also be a plastic, and I want you to see the typical property of glass, spectral property. So, if you are in a wavelength range below 2.7 micron, then the absorptivity of glass is very small, 0.07. Transmittivity transmit most of the radiation in this region below 2.75, and deflection, which is bound to occur is order of 0.08, sum is equal to 1. This is in the region where visible and infrared, but you go to further up in the infrared beyond 2.7 micron, the situation changes totally. Reflectivity increases to 0.1, your absorptivity increases to 0.9 and transmittivity is 0. So, this property of glass is what we try to exploit in a solar collector. So, it is transparent to solar radiation, transmits almost 85% or can even be more, while it is opaque to radiation from the absorber. Absorber is typically a temperature of around 70, 80 and 90 degrees centigrade. So, at that temperature the absorber emits radiation in the range from 4 microns to 100 micron, in which range there is no transmission. So, interestingly, the glass surface which is so transparent to the visible is totally opaque in the infrared. So, it behaves like a blackboard in the infrared, but it is totally transparent in the solar region. So, these are the kinds of unusual surfaces which give us a special advantage for designing collectors which will allow the radiation from sun to come through, but the radiation from the plate is reflected back. So, this is the advantage of non-gray surfaces which have very different properties between, for example, absorptivity is 0.07 below 2.7 micron and is 0.9 about 2.7, and the transmittivity is essentially opposite. So, this is what is used in solar collectors to trap the solar radiation within the collector and hence increases temperature. The same thing happens on earth. On earth, the surface of the earth and you have an atmosphere containing gas like carbon dioxide, water vapor, methane, which are all almost transparent to solar radiation, but opaque to radiation from Earth's surface. So, the presence of these minor gases, they are all minor. Remember that Earth contains mostly nitrogen, oxygen and argon. So, these three gases make up almost 99.9% of the Earth's surface, but they play no role in radiative transfer of either the sun's radiation or the Earth's radiation. It is the minor gases which constitute a very small concentration. They are the ones which are influencing the Earth's climate because of their ability to trap it. So, because of the presence of these gases, methane, I will also add ozone. All these are gases which trap Earth's radiation. The temperature, the surface temperature of the Earth is higher by about 30 centigrade. So, this is a huge warming that has occurred on Earth due to naturally occurring gases like carbon dioxide, water vapor and methane, but over the last 100 years, we have increased CO2 by around 100 ppm, and this has increased the temperature by around 0.7 degree centigrade. This is because higher amount of CO2 traps more of the Earth's radiation, and this leads to chain reaction by which water vapor also goes up, ice melts in the polar region. All these combine together to increase it by 0.7, and the prediction is that in the next 100 years the temperature may go up by another 4 to 5 degrees. So, this shows the power of the non-gray surface that exists in the Earth's atmosphere, and so we will look at these issues later when we talk about gas radiation.